Okay, I think probably waited long enough. So thanks for coming. It's a pleasure to be here. My name's Dr. Tom Tranter. I'm a postdoc at UCL. And thanks for the organisers of this webinar for inviting me along. Just a couple of housekeeping notes. We are recording this webinar, and it will be uploaded to YouTube as part of the series hosted by UCAN+. And there will be opportunities to ask questions. As there's a relatively small number of us, I think probably what I'd prefer to do is when I've finished the presentation, I'll run through and make everyone a panelist effectively, so you can speak directly, and it will just facilitate conversation a little bit easier between us all. But as questions pop into your head, feel free to write them down into the Q&A box, just for your reference, or for mine, just to see if there are any good questions. and then we'll go from there. So I anticipate that the presentation will be about half an hour, and then maybe slightly longer, and then we can get into some discussions, and hopefully we can have some interesting back and forth. So basically my background is that I'm not really an acoustic specialist per se. So the reason I joined up to this network is to interact with you guys as much as possible, and hopefully forge some interesting collaborations in the future. So that's kind of what I'm hoping to get out of this. So the outline of the talk is in front of you guys. It's acoustic diagnostics for state estimation, quality control, and failure prediction of batteries. I'm going to cover a little bit of the motivation and background. I was assuming that most of you would not be sort of electrochemists or battery specialists, so apologies if you are. I'll be covering some battery basics, but I think it will just help set the scene. I'll be covering a complementary technology that we use a lot in our group, which is X-ray computed tomography. And then going into some modeling and a bit of a literature review of acoustics and batteries, and an overview of the work that we've done in our group so far, and outlining some future plans. And then hopefully we can have a discussion at the end about maybe ways that we can collaborate in the future. So first of all, a little bit about myself. As I said, I'm a postdoc researcher in the Electrochemical Innovation Lab at UCL, which is part of the Chemical Engineering Department. And that's a collection of about almost 100 researchers now, including postdocs and PhDs and full-time academic lecturers. And the guys that run the group are a couple of professors called Dan Brett and Paul Shearing, sorry. I received my master's in physics from Warwick University in 2007, before spending a little time in industry as a software developer. And then I returned to academia and did a PhD in Leeds, and finished that in 2017. And I was actually investigating fuel cells and porous materials. And then since finishing the PhD, I've done a couple of postdocs, one in Canada and one now in UCL, and that's focusing on batteries, and really kind of a whole range of scales are involved in battery research. And I'm more kind of interested on the applied sort of larger side of things at the cell and pack level. And one of the diagnostic techniques that we use in our lab is acoustics, and that's what I'll be mainly talking about. So here's the group. As I said, quite a large number of researchers. Dan and Paul in the middle there, looking happy. And we've forged a large number of collaborations around the world and with other institutions and synchrotron organizations, national physics laboratories, and we're producing quite a lot of really good work in the kind of electrochemical space, mostly concentrated on batteries and fuel cells, but also involved in redox flow, electrolyzers, supercapacitors. So anything where charge moves about, basically. And I'm personally sponsored, along with a lot of my other colleagues, by the Faraday Institution, and specifically I'm working on this multiscale modeling project, and that involves 9 universities with 14 industrial partners, quite a lot of funding to date. And we're largely developing modeling platforms to answer research questions in the battery space. 3 of those platforms so far have been kind of released to the public, and I'm mainly involved in the development of the first one. You see there Pieband, which is a Python package for battery mathematical modeling. And I'll come on and talk about that in a bit more detail in the upcoming slides. But the goal of the multiscale modeling project is to basically to help simulate an electric vehicle battery pack. The project considers a range of length scales from atoms all the way up to pack level kind of thermal and computational fluid dynamic kind of stuff, and also across a range of time scales, going from seconds to years, as some questions within the battery space involve kind of lifetime cycle studies, and those kinds of simulations require a lot of optimization in order to get results in reasonable amounts of time. So Pieband actually is sort of a one-dimensional model framework, really. It's very fast. It can simulate a single discharge of a battery in about a few milliseconds, and we can use that framework to kind of do material exploration and parameter estimation and sort of road test models that are going to be running for over long time scales. So this is a video from a TUM, just basically showing the basic components of a battery. It's just a single layer battery with two electrodes. So on the anode, on the left, you have particles that are made from graphite, typically. Sometimes you have a little bit of silicon sprinkled in there. And on the right, you have some sort of transition metal. And I'll come on to some of the typical chemistries. In the middle, the white region, you have a separator. And connecting the system, you have electrolyte in which the lithium ions actually flow. So the lithium is hosted within the active material on each electrode, and it's an intercalation process that occurs where ions intercalate in and out and move across the cell. Electrons flow the other way in the redox reactions, and as it discharges, the ions move from the anode to the cathode, and then the reverse process happens. We don't need to watch the rest of that. Basically, as you charge, the ions move from the cathode to the anode, changing the voltage of the cell. There are 3 types of lithium-ion batteries that you'll typically come across. The ones that you'll see in your torches and such, the cylindrical size, the ones typically used in the automotive industry tend to come in standard formats, and they're sort of they're described by numbers that relate to their diameter and their height. So this 18650 here is 18 millimeters in diameter and 650 millimeters in height. 65 millimeters, sorry. Don't know why there's an extra 0 on the end there actually, but that's the way it goes. And then that tends to be the kind of smallest cylindrical cell that's used in sort of battery packs that get put into cars. Tesla, for example, I think now uses a slightly larger one as standard, a 21700. And within one of their more powerful engines, you can get in the tens of thousands of these cells, all combined into modules and then into the large pack. But the individual batteries themselves tend to be on the smaller side for used individually for smaller applications and range from a capacity of 1 to 10 amp hours. Going up in size, you have prismatic cells, and they have a hard casing. And they're a bit more robust, and the form factor being square allows for a sort of better energy density at the pack level, but they're more expensive than on a sort of per unit basis, and they're typically used individually in phones, but also they can be formed into packs as well for electric vehicles. And unlike the cylindrical cells, which I guess have the standard sizes because of the more mass-produced aspect of their production, the prismatic cells tend to be of all sorts of shapes and sizes. So there's no real standard, and I guess that's an advantage for some electric vehicle makers, because the space that the batteries are going to be put into are not always, a standard shape. They might have to fit around all sorts of other components. So they tend to be bespokely designed for certain applications. And then the last type is a pouch cell, which is sort of capacity-wise in the middle of the other two. And it has a flexible casing that's typically connected directly to the positive tab, and that makes it live, actually. So you have to be a bit more careful when you're handling them sometimes. And again, these kind of come in all the different shapes and sizes, but they are well, they're the most efficient space-wise because of the lack of the extra hard casing. However, they do have some issues when you start to use them. They can sometimes swell, and thermal issues can occur. But they have their advantages too. So being flexible and in their design. And within the cells, you actually have what's called a jelly roll. So in the cylindrical cell, this is literally the two electrodes that I showed in the video are actually these long sheets, which are for the 18650 can be about 1 meter long, and they're placed next to each other and rolled up into this kind of, that's why they call it a jelly roll, and then stuffed inside the can. And the same thing happens in the prismatic cells, except instead of a cylindrical shape, you sort of have a squidged oval shape. And then the other way you can do it is actually to have a layer. So you can see the prismatic one is a similar but squidged shape. And then the pouch cells tend to be all layered, and all of the current collectors tend to be sort of welded together, and that forms the tab. And when we are doing our acoustic studies, we are tending to use these pouch cells as it's more or less the simplest system that we can study in the battery world, where you have your transducers emitting sound directly from the top to the bottom, hitting these layers in a sort of planar way. It produces the kind of the signals that are easiest to interpret, and that's kind of why we've started off using the analysis on these ones. But obviously, we can't just limit ourselves to studying pouch cells only, because there are lots of applications where these aren't used. And so one of the things that we want to develop and sort of hone in the future is our analysis techniques for these sort of these rounder cylindrical and prismatic designs. As far as battery chemistry goes, these are a few examples of different materials that can be the host material for the lithium ions in the cathode, and they have their different benefits. You can see on the right you have these spider plots. Some chemistries are better for specific power, some are better for lifespan. The main two that are getting sort of a lot of attention and commercial use now at the moment are LFP and NMC. And LFP was pretty fashionable a while ago, and then it seemed like it was not going to be used much at all because it had a lower voltage. But the lifetime and performance that you can get from LFP is sort of bringing it back into fashion. And now I think Tesla have plants in China that are really focusing on LFP, and they've overcome some of the power and energy sort of deficiencies by making optimizations at the pack level. And then the NMC is basically the most popular for sort of the widest range of applications, because it sort of ticks most of the boxes and it has a high voltage compared to some of the other chemistries. However, the NMC, the main drawback with that is the lifespan. So you get particle cracking and you get loss of active material that reduces the capacity. And especially with high nickel content. So this NMC is nickel, manganese, cobalt. And you may have heard of some of the issues with the cobalt supply chain as well, being largely concentrated in just a handful of slightly unstable countries. There's now, economic and I guess geopolitical reasons why NMC is becoming less popular. So on the anode side, typically you'd be looking at graphite, and more often that graphite is going to have a sprinkling of silicon in it, and that silicon increases the capacity, but it then also has a few issues as well with lifespan. So the silicon actually undergoes quite a large volumetric change as the lithium intercalates inside it, and then that causes mechanical issues within the cell, and you get some degradation associated with that. So it's kind of a large area of research. And one thing I haven't included here is pure lithium metal anodes, which is sort of the holy grail, I guess, of anode research. But I don't really have time to go into the reasons why they're not really commercially viable at this point. But essentially that would give you really high energy density and a good cell potential. So the current research focus within the batteries is, as I've sort of touched on with those spider plots, extending lifetime, improving safety. The EV industry is very, very keen on fast charging, because obviously as a consumer, you don't want to be hanging around for ages charging your electric vehicle and not driving anywhere. Thermal issues and battery management, recycling, and then bringing on new chemistries. And these are sort of, all of these sort of research goals in a way can be studied with the sort of diagnostic techniques that we're developing. So lifetime, we can look at the effect of the change of materials over the lifespan and see whether any sort of traces in the acoustic signals could develop over time that we can identify. Safety, we have gas evolution inside the cell, and we can pick that up with acoustics. Fast charging, the acoustics signatures are sensitive to temperature, and with faster charging you get higher thermal output. And then maybe not so much recycling, although acoustics can be applied to second life applications, so very quickly to sort of scan the cell instead of spending time scanning it in some other way in a tomography machine or just cycling it a lot. We found that the acoustic technique can sort of pick up cells that are going to be particularly bad for second life uses. So when they come out of cars, they might be repurposed for stationary storage applications. Recycling, as in tearing the cell down and getting the materials and sort of making new cells, maybe not so much there. And then new chemistries. I mean, this is something that we're going to touch on in the later on, but the actual material responses to the acoustic signals is kind of not that well understood. At the moment, there's not too many fundamental studies on sort of changes in modulus and things like that as the materials change themselves. And so new chemistries are going to, we're going to basically increase that problem. So as I said, the materials are in the process of charging and discharging the battery involves intercalation. Basically, I won't dwell too much on this slide. There's a few too many words on it, but the compound should have the following characteristics in order to make it good for that purpose. A large amount of lithium should be able to be inserted into these materials to increase capacity. The insertion extraction process should be reversible with minimal changes to the host structure over the entire range of lithium insertion extraction. There should be some chemical stability for the reactions, and the compound itself should have good electronic and lithium ion conductivities to minimize the cell polarization. So it's essentially to maximize the amount of energy and power that you can get out of the cell. And also the voltage profile should be relatively continuous, as they make the batteries harder to predict what they're going to do in real life applications. And from a commercial point of view, it shouldn't be too expensive. So I think in terms of the materials that could be used as intercalation hosts, you know, there's already quite a few options out there, and new ones coming on board are probably going to involve not necessarily hosting lithium ions as the charge carrier, but perhaps some other sort of battery that may involve sodium or some other process that will partake in a redox reaction, but not necessarily a standard chemistry. But this is just to kind of give you a feel that, you know, when you hear about a lithium ion battery, you know, it's not just the lithium that it's important, it's all the other stuff that goes into it, and there's a whole bunch of different materials that go into a battery, and a whole bunch of different options. So that kind of presents a challenge in itself for diagnostics and for kind of making predictions about how these materials are going to behave. And also they all have different responses in terms of their operation. So certain chemistries are going to produce more heat, and temperature is again quite important for understanding what's going on acoustically. And this is just to demonstrate that the intercalation process is not always the same process with your different materials. So you have these sort of three, I guess, classes of crystalline structure. You have the layered materials, spinel and olivine, and they will all have you know, a different response in terms of their mechanical properties as you put more and more lithium in. So it's just something to kind of bear in mind when doing the acoustic characterization. So I mentioned this already, that we do a lot of X-ray CT in our lab, and it's a very complementary technology. So this is where we actually have the bulk of our expertise in our group, to be honest. And we've been scanning batteries and fuel cells for quite a few number of years now. But there are a few drawbacks with that, in the sense that, you know, we have these very, very expensive machines, and they are it takes time to take the results. So one of the main motivations behind the acoustics is to sort of reduce cost and increase speed of our diagnostic capabilities. But that, having said that, they are complementary technologies. So it's always good to sort of know what the domain is that you're going to be you know, pulsating through, and you can make more informed sort of models and decisions. So a little bit of an overview of CT. Basically, as these batteries are fundamentally a multi-scale device, we can probe them on all these different scales. You have, down at the micron level, you have the particles, sort of tens of microns. You have transport through a porous material, which is made up of particles and binder materials. And then at a slightly larger scale, you have whole electrodes, and then whole cells and packs. And we can probe the cells at all of these different scales. So some of the key things that we look at with X-rays are the failure mechanisms, degradations, and capacity limitations of these cells. And some of the advantages of the technique is that it's non-destructive, and multi-length scale and multi-time scale. So we have 3 machines in our lab, in the Electrochemical Innovation Lab at UCL. The one with the sort of largest field of view is the Nikon, and we can actually now scan a whole battery in about a minute, and we find that the quality of the image at that level is acceptable for some of the analysis that we undertake. We have a slightly more better resolution machine in the X-Radio Versa, and we can zoom in to sort of the single layer images for that one. And then for the particle level, we have the X-radiate ultra, and that can get very high resolution of sort of hundreds of nanometers. And just to put that into perspective, when you do these kinds of studies, you might not have these sort of lab scale facilities. You might go to a synchrotron or something like that. And you have this sort of plot of what kind of spatial resolution you can get and the time it takes to take the image. So you can see that R3 machines are sort of on this end of the spectrum here in comparison to some of these other facilities. But we do commonly work with Diamond and various other ones to get synchrotron data when we need to take very sort of highly temporally resolved images. So what do we do with these images when we've got them? Well, Dr. Shuken Liu is a distinguished member of our group and has done a lot of modeling work using image-based modeling of lithium-ion batteries. And I just got a really nice video that he's put together just to demonstrate kind of all of these scales working together and what we can learn and resolve from them. So here we have the whole cell being scanned, the different components. And then we can zoom in and we can see all of the layers. On the left, you have the cathode, in the middle, the separator, and on the right, the anode. Once we have the image, we threshold it to resolve the different phases. And here you can see the solid phase. And you can see that each one of these materials is a porous material, which would be filled with electrolyte, where the ions are transported. And you can get statistics on the porosity, pore size distribution, tortuosity, and then on the active material side, you can look at things like shape factors, and again, particle size distributions. And then we can simulate electron flow through the solid and lithium ion flow through the electrolyte, and participating at reactions at the interfaces, at the particle surfaces. And we can resolve the state of lithiation at various states of charge. And here's a few figures from a paper that came out last year in Nature. And what Shuken actually did was take these baseline images, conduct simulations, and then make adjustments, artificially, if you like, to the images themselves to sort of adjust particle size distributions and sort of microstructural effective parameters such as porosity and tortuosity, and then rerun the simulations and kind of look at the effect on the capacity and specific power of the cell. And it's a very interesting paper. I encourage you all to go and look at it. So on the larger scale, we also have done quite a bit of work looking at these jelly rolls and layered structures in other types of batteries. We can pick out all of the layers pretty easily. They attenuate the X-rays in different ways, and so the different materials appear as different colors. The brighter one is the cathode, and in the center you have a current collector running through it. And then the darker one is the anode and another current collector, and that bright current collector is copper and the other one is aluminium. So you can build up these images and then do analysis on how these layers are going to be sort of changing over time. As the cell charges and discharges, you get slight expansion and contraction, and that of course changes the acoustic properties as well. And another technique that's been used by our group as well is neutron imaging. So this is kind of a cool video of a cell exploding. So we can actually do pretty high time resolution, and this is over just a few seconds, a cell being abused and undergoing a process known as thermal runaway and venting through the top cap. And this was all captured with pretty high resolution. So this is one of the key concerns for safety in the battery community is thermal runaway. When you heat a cell or when you penetrate a cell with a nail or something, you short circuit and you get this very high discharge of the cell, which produces a lot of heat. Once the temperature reaches a certain critical point of around 120 degrees, you actually get the you get reactions in the electrolyte, which then produce heat themselves, and you get this runaway kind of positive feedback, and very quickly the cells can explode. So thermal management is key. So with these sort of cell level images, we can see that as you age the cells, you can see that it clearly changes over time. Certain effects basically make this worse or better. So sometimes a cell will have a mandrel in the center, and that will actually sort of pin the electrodes into place a little bit better. But comparing the black and the blue images here, we actually find that you get these kind of pinch points that propagate in the same radial position. And you can see that in this nice image here over time. Well, actually, that's not over time. Sorry, that's just rolling around the in the radial direction. I'll show that again. So you can quite clearly see actually in this image that at this particular angle theta, these layers have kind of collapsed in on themselves, where they're not being supported by anything in the center. However, this blue region here is the sort of outer layer, and in this dividing line here, you actually have a central tab. So to actually extract the current out of the cell, the foils are connected to these tabs, and typically for smaller cells, you'd maybe only have one at the inside and one at the outside, but for higher power or higher energy, larger cells, you might have tabs in the middle that kind of keep things in place a little bit better. But we're doing quite a lot of studies on how these sort of macro level sort of changes take place, and they actually, as you might imagine, affect the cell capacity quite a bit. As the layers pull apart, they're less well connected together, and you need good connections for the ion transport to take place, basically, and for electron transport also between the current collectors and the electrodes. And that brings me on to the next section, which is modeling. So as I mentioned earlier, I've been involved in battery modeling as part of the Multiscale modeling project within the Faraday Institution, and I've been developing this package in Python called Pieband. And it's a physics-based DAE solver, basically. We have various different battery models. The most sort of complex one is this Doyle, Full and Newman model, the DFN, which was it's about 30 years old now, but it's essentially named after the three guys that put the model together and came up with it. But we can solve that model now in like less than a second for a single battery, which is a one-dimensional model, and we can resolve essentially the lithium concentration within the cell, and also the temperature and the potentials within the cell. And we also have some even faster reduced order single particle models, which can run in a number of milliseconds. And with this framework, we can replicate all of the kind of cycling experiments that you might do in the battery lab. So for characterization of your batteries, such as constant current, constant voltage, or GITT, which stands for galvanostatic intermittent titration technique, I believe. It's basically a way of discharging and interrupting the current in order to get a measure of the resistances, the internal resistance of the cell, as a function of state of charge. So with this framework, we can compare different things. We can compare the different chemistries, how they behave together. This is actually comparing a different particle level model of intercalation. This one is cycling the battery. Just constant current, charge and discharge at a fixed current of 5 amps. And you can see the two things that are probably most important for us studying the battery with acoustics are these negative particle concentrations and positive particle concentration as they go up and down. And this on the x-axis is, if you imagine drawing a line between the center of the anode and the center of the cathode, that distance there as you go through this, through the cell, through the separator. And these are lithium concentrations as they intercalate. This is cycling up and down, and this spatial variation in the x direction is essentially due to the transport limitations within the pore space itself. So if ions were able to move very freely about the cell, you'd expect these to be sort of more flat lines. And that's what our reduced order models end up predicting. We don't actually resolve this concentration in the x direction with the simpler models. But you can see here the voltage of the cell cycling up and down. And typically when you look at a cell and you want to know any sort of information about its state of charge or state of health, you'd look at the voltage and you'd do Coulomb counting on the current, which essentially just means that you're measuring the current over time and counting up how much charge must have passed back and forth. With the modeling, you can get more details. And with this change in particle concentration, you're changing the properties of the materials. So you're changing the density and also the Young's modulus, and that's going to affect the acoustic response. And what we actually see as we charge and discharge, we have this like seesaw of ions going back and forth. We can actually detect that with acoustics, even though the length scales are very small. And here we have just a thermal simulation with different heat transfer coefficients. And you can see that actually, well, it's the same current for each of the cells. The voltage changes a little bit, not much in this particular example, but we're getting massive differences in temperature actually. And these concentrations aren't changing much, but as the stiffness and the thickness of the cell are also a function of temperature, we actually get quite a big variation in acoustic response. So in a sense, we can use the acoustic response as a sort of internal temperature sensor, which is really cool because there's kind of a lot of interest in thermal gradients within these cells, as the thermal, not just the absolute temperature, but the gradient itself will affect where certain regions of a cell will be degrading faster than others. And so actually this is quite a promising thing, that it's sort of annoying a little bit that the acoustic response is temperature dependent, but if you can control the situation enough, you can use it to your advantage, I think. Now this is sort of what I've been doing over the last couple of years. I've been taking these tomography images and making models out of them, and using the CT image directly. I can essentially use this kind of like resistor network approach, where I'm dividing up the cell into different regions, and I'm applying a Pieband model at each one of these little interconnections, but resolving the global current and the heat transport at the cell level. So this is going to be useful to integrate with the acoustic models that we'll be developing. So as we can capture those different changes in states and changes in temperatures with this model, we can then start to predict what the acoustic response is going to be throughout the different spatial regions of the cell. And we can resolve temperature gradients with different kind of cooling scenarios, where if you have a battery pack that's in an EV, you might have cells that are all lined up together, but you have a cooling jacket that's kind of snaking in between them. So you can simulate things like only cooling a third of the surface of the cell and seeing what effect that might have on the temperature. And you can also, with this framework, look at tab placement. So how the temperature is affected and how the current uniformity and the sort of local state of charge is going to be affected by introducing different numbers of tabs. So it's proven to be like quite a useful framework so far. And we're only now just starting to integrate it with acoustic analysis. So that was a lot about batteries. And yeah, I've been talking for quite a while. I do apologise. The motivation, as I've touched on before, is that the acoustics can be fast, non-destructive, and cheap. And the operating principle is that you pass a signal and you get a response back from the different layers. As you can see, they're made of different materials. They have different densities, and you'll get reflections. And by analyzing those reflections, you can tell what the state of the system is at different points. This is kind of a cool video, just showing basically that the state of the battery changes, and it has an acoustic response. So this is changing this coefficient of restitution of the battery as it changes, and that's going to change the acoustic response. And the idea is that actually, as the particles intercalate, they expand a bit, they become more dense as well, and that creates different kind of stiffness pathways through the materials. We've recently published a literature review. It covers all sorts of electrochemical devices, but also I'm just going to focus on batteries. And to date, there haven't been really a lot of studies that have been conducted on electrochemical devices. It's still a pretty young field, so there are opportunities there. But essentially, there's two branches of research. One being acoustic emission, which is sort of looking for these kind of cracking events that are going to be emitting pressure waves, and they would typically occur with a higher frequency at certain stages of the charge and discharge as the materials reach a kind of critical stress point. We're kind of less interested in these types of acoustic emissions for sort of ongoing diagnostics. We're more interested in this ultrasonic testing sort of aspect. So where you've got transducers either on one end or both ends of your material, and you're passing this acoustic signal through and seeing kind of what comes back. And actually, what the important kind of information would be the time of flight of these reflections. So as the density and composition changes of each of the materials, you get these shifts in time of flight, and you can very readily associate that with certain sort of states of the battery. So here we have a study by Hazai, which came out a few years ago. It's part of Dan Steingart's group, who's a professor in New York, and he's done a lot of work on acoustics and batteries, kind of a pioneer in the field. But this was a really influential paper, and it's essentially just a 1D model, charging and discharging the battery, changing the state, and seeing this slight change in time of flight from the reflections from the acoustic signal. So you can kind of see it. This is from the supplementary material from that paper. So I've just incorporated that into this presentation just to kind of show the signal, the reflected signal and the transmitted signal there over time as the pulse propagates through. We can see that going. And this is from a more recent paper from a group in Sheffield, and they did a really in-depth analysis of sort of signal analysis and ways that you can process the information that you're getting out of these batteries. This is a really nice little demonstration of just what the effect of changing a particular property has on the signal that you're going to get back. So we can see here all of the properties, the acoustic properties of the different materials, elastic modulus, density, and what that eventually has an effect on the wave speed. But just comparing what happens when you change the separator wave speed. So the separator is occurring at these light spots all throughout the cell, and this is a sort of 20-layer cell. And if you compare this signal with that signal, you can see that you've halved the wave speed just on this like very small layer, and you've completely changed the signal response. And there's a little bit of tuning, I guess, that has to go on in terms of the frequency and sort of, well, using the same acoustic setup for different cells is not always going to necessarily be the case. To provide you with good signals, I guess, is taking a message from this particular figure or image. But yeah, it's a very good paper, and we hope to be sort of producing very similar sorts of results for our batteries that we've taken images of in our lab and processed. And what we have, the sort of aim of the physics-based modeling is to kind of back calculate material properties, I guess, over time in different conditions from these signals. So we want to effectively run this one-dimensional model for parameter estimation purposes. Experimentally, we've done quite a bit. This was a study from a few years back where we essentially divided the cell up into this different sections and placed a transducer at each one and monitored the response at different points. And you can see the effect of different kind of macro level features, such as the tab placement is very affecting the signal quite greatly. You also have, it was one of these rolled designs, a prismatic cell, and you have sections in the middle where there may be in better contact than in some other certain areas, and that also affects the kind of signal you get. So it's quite a complex problem when you drill down and try and start using it in a practical sense. So you have all these different features that can affect your signal, and you can't really just apply one sort of algorithm or one equation in order to be able to interpret your signal. You have to sort of adapt it to the different regions and bespoke kind of features of the cell. Having said that, you can observe general trends. So this one, for example, was an acoustic response to a cell that was undergoing thermal runaway, and this was a pouch cell. So as the thermal runaway was occurring, you actually had gas generation from these reactions in the electrolyte, and this gas was actually pushing the layers. So I mean, you would be able to see that in the lab. You'd be able to see the cell expand, but you can actually detect the sort of onset. Like the acoustic technique is much more sensitive than the eye is, and then also the temperature sensor was, because if this runaway event and this gas production is happening in the center, the acoustics is going to be able to pick that up straight away, whereas it takes a little time for heat to kind of propagate out and affect the surface temperature. So it's like an enhanced safety feature that you might be able to use acoustics to do this sort of runaway monitoring, and hopefully we'll be able to build on this and show more work in the future related to that. We can also do defect detection. So here we actually got a cell and made a hole in the electrode, and we can clearly see that the acoustic response is different there. So this could be a technique that's used for kind of quality control as batteries are being made. And then here's one that we didn't purposefully insert a defect, but we found one anyway. So just proving the technique. And we can also use the acoustic response in some of the formation and fabrication processes. So as electrodes are drying out, their material properties are changing, and we can kind of track these peaks, which we believe are multimodal. So we believe that as the material is changing, we have these modes of acoustic wave propagation that are occurring through the electrolyte and then occurring through the solid. And you can kind of see that as they're definitely two separate phases, there's kind of two peaks, and then as it dries, the solid becomes dominant, and it more or less all of the connected pathways are through the solid, and you just have this one peak. So that was a kind of an interesting study, but more work needs to be done on understanding these phenomenon and modeling at these kinds of scales. And then this is something that we're exploring with a commercial partner, is actually acoustics on the production line. So you can see that with the manufacturing of batteries, they go through all these different stages, and essentially we could probably probe the battery and detect whether something's gone wrong just by comparing it to signals of cells that were kind of passing quality, in order to early sort of identify the cells that are going to be bad cells and prevent them from going through the latter stages. So formation is actually a really long process. They actually have to cycle the cell very slowly for a number of days and then leave it to sort of settle, if you like, and that takes a lot of time and energy in order to do that. So, and this is kind of where they really get this is kind of like the traditional point to implement proper QA, but if we can implement it earlier on, we'll sort of save time by eliminating those bad cells. And yeah, we can detect changes in the acoustic response at various stages. I'll skip through this now because we're kind of running out of time. So far, the modeling that we've done has been two-pronged. The physics-based ones, where we're setting up a 1D simulation here, and you can just see that these layered materials produce these more complex responses as you increase the number of layers. So I think these models are going to be really key for kind of unpicking some of the experimental data and doing that reverse engineering of the material properties. And then the other arm of the modeling has been machine learning based. So in the lab, we actually cycled a cell under different temperature profiles. Cycled the cell under different cycling profiles, so at different rates. This C/5, C/2, 1C. This C relates to the capacity. So 1C relates to the current that would discharge a cell completely in 1 hour. So 1 capacity, 1 hour. So C/2 is half of that. So that will take 2 hours. C/5 is a fifth that will take 5 hours. So this is the slowest one. And just applying sort of standard kind of lab-based kind of regression, I guess, varying temperature and varying state of charge, we can get reasonable predictions for what the state of charge is purely from the change in time of flight of certain key peaks in the signal. However, doing machine learning enables us to improve on those predictions. I'm not going to have time now to show these videos, but this is essentially this is the raw acoustic signal over time. So this is charging and discharging at slow rates, and you can see it kind of wobbles. It's this peak, this final echo peak it's kind of referred to, which is the signal going all the way through, hitting the back of the cell and coming back. And when you're doing the analysis by hand, if you like, we're just kind of picking that one peak and looking at the shift in time of flight there. With the machine learning, we can take the whole waveform as our feature input, and we can actually we can get information about the whole cell essentially. But as this is going quite slowly, and you can see the peak is not shifting too much. If you go later on, we're now at higher discharge rates, and you can see this peak is really moving around. And this is a combination of maybe more stressful material changes, but also increased temperature. So as you discharge and charge faster, you're going to be producing more heat. And so this is kind of work that's been submitted, but not published yet. But we've looked at various different ways to analyze the data with machine learning, different combinations of numbers of layers and things. And also doing this analysis on the whole feature, we can look at a Pearsons coefficient, which is correlating, is this feature correlating well with my output, with my state of charge? So we can see that we kind of get this, yes, these particular features are correlating well, they're changing with my final output prediction, and some are not. And so this one here is actually kind of like noise. This is from the transducer before it even hits the cell, and that's not changing at all. So it's a bad correlation with state of charge as it changes over time. And then we have essentially like a very good mean absolute error over as you increase the number of training samples. So this is essentially just increasing the data set. So the data set we have is reasonably large. I guess it was cycled 5 times at each state of charge, each C rate, sorry. So 15 cycles, which is not, I guess, insignificant for building a kind of predictive model, but it's not too bad. And there's opportunities to improve computational economy, and possibly look at different feature selection to reduce the computational time. And finally, one of the members of our group, Harry, has been looking at actually the thickness change in these pouch cells, and there's quite a high correlation there with state of charge as well. And so that's just another thing to bear in mind when doing these modelings and analyses on the acoustic, on the waves, that the actual dimensions of the whole cell are actually potentially changing quite a bit as well. So it's just a kind of another complementary technique that can help us decode the data, I guess. So quickly, our future plans. We want to continue doing what we're doing, investigating degradation, cycling at low temperatures, thermal abuse. Not only do we want to predict state of charge, but we want to predict state of health. So essentially, how good is this battery compared to when it started? And we want to develop the modeling expertise alongside the machine learning. And it's going to be a data problem because, you know, we can sample these cells at incredibly high frequency and gather all this data over any number of cycles. How we actually process all that data and make kind of meaningful insights is going to be the biggest challenge. I think it's going to be a combination of both types of modeling approach to eventually get there, and maybe even a fully resolved microstructural model as well, in order to understand the sort of more exotic changes in the signal. So finally, thank you to all my colleagues and my collaborators in the Electrochemical Innovation Lab. These guys have all been involved in the work that I've been presenting today. With that, I'd like to say thanks for your attention, and let's see if you've got any questions. Okay, I can't see any in the chat. What I'm going to do, I see that some of you are raising hands. Can I just select all of you and make you, sorry, I'm a little bit rubbish when it comes to Zoom. Right, allowed to talk, there we go. Hi, Rob, what's your question?
Yeah, thanks so much, Tom. That's been really interesting. I was quite curious that you sort of viewed the temperature issue as a positive thing rather than a negative thing. We've been struggling because the temperature is changing the properties of the material, the acoustic properties, and the state of charge is changing at the same time. So you've got two things happening at once, and trying to separate them from just one acoustic signal is quite a challenge.
Yeah.
You sort of kind of indicated that you thought that there were some possibilities around measuring this temperature change. I wonder if you could say a bit more about what that might be.
Well, I think, yeah, you're right, it's a challenge, but if you can solve the challenge, then it's an opportunity, because you'd be able to predict temperature internally for which is what are the alternatives to be able to do that in terms of a battery that's kind of being used live in a real world application. There's almost no other way to do it, I guess, without embedding a temperature sensor inside the cell. So I believe that you could get the predictions good enough so that if you had other kind of validation tools for evaluating state of charge, you could then sort of fix that and then focus on temperature variation as a way of using your acoustic method to predict that. So that's sort of what I was getting at. It seems like a problem because the signal is very temperature dependent, but maybe you could turn that around and use it as an advantage. If you can nail the other predictions, then you can predict temperature with better accuracy.
So I guess if your model is reliable enough, your model is accurate enough, you could separate out the material properties parts. Is that what you're thinking? Your physics models are good enough that they can tell you exactly what your acoustic properties are, and hence you could extract that to be left with the temperature effect.
I think so. Yeah.
Yeah. And sorry to another sort of rider to that question is the sensors themselves are temperature dependent, and they're going to change. Their output of a piezoelectric material is going to change as well with temperature, which is also going to be an issue when we want to put these things in the oven. And is that something that you've got any thoughts about?
Yeah, that's. I mean, I suppose you just have to account for that in some other way, right? That's not something that we've particularly accounted for in the data individually. I guess it's just kind of baked into the sort of signals that we're getting at the moment. But it would be worth doing a sort of, yeah, like an extra bit of an analysis on that to account for that effect. Yeah, it's a good point. Was there someone else that had their hand raised at one point? Okay. Valerie Pinfield, thank you. You have to leave, but I would like to have a conversation with you about this. Okay, cool. John has to leave as well. And Bo Lan, okay. Hi, Bo.
Hi, Tom. It's a very good presentation. Thank you very much. I'm just want to accent on top of Rob's question. So if you have the coupling of the temperature and state of charge change at the same time, if we are able to get acoustic signal throughout of the thickness, can we assume that the state of charge is consistent throughout the thickness and the acoustic signal change is purely affected by the temperature difference throughout the thickness? Is that a reasonable assumption to make?
It depends on the cell. Is the short answer, I think. So certain cell designs, like certain cell sizes as well, I guess, are going to be kind of more conducive to having a homogeneous distribution of states than others. When I showed you the pictures of the jelly roll, it really does depend on the sort of extra features of the cell, like the number of tabs, for example. So if you have just one tab on each electrode, that current is having to pass all the way around the spiral. So regions of the cell that are further away from those tabs are going to be experiencing a different sort of environment and a different state of charge to regions that are closer to the tabs.
Okay, so in that, sorry.
Well, I was going to say, so that's when you're operating. When you relax, theoretically, it should kind of self-balance. So I guess when you're doing your kind of calibrations to kind of extract your material properties, you're going to have to be introducing periods of relaxation in order to kind of address those heterogeneous sort of states.
Okay, so in that sense, is it right to assume that the pouch cell, which has the all the current connectors wired together, so the passing routes will be similar, would have more homogeneous state of charge?
Yeah, I think so.
Okay. Okay.
Again, though, those cells can have sort of very large form factors. So yeah, you can introduce heterogeneity there as well.
Okay, understood. Thank you very much.
Yeah, I guess that's it. If no one else wants to raise their hand, I hope you guys found that interesting and I didn't ramble too much.
Tom, can I ask one more?
Yeah.
Is the recording going to be released, and where could we find it in the future?
Yeah, I think it's going to be on YouTube actually. I don't know if I can see Zoe online anymore, but she was moderating.
Hi.
Yep.
Sorry, so to just jump in there, yes, all of the UCAN webinars are put on our YouTube channel. So that's the Acoustics YouTube channel. I'll find the link and I'll put our channel in the chat. So yes, all of the series are there.
Great, thank you very much.
All right. Well, thank you for your attention. And if you have any other questions, I guess will we be making the slides available as well, Zoe, or just the video? I can put my email address in the video, or as a comment there, or if you have a mailing list, I can put it there.
Yeah, we don't tend to make presentations available. We've not done that previously. I think, yes, if you're happy to do that via email, that might be easier for us.
Okay. Well, yep. Once again, thanks, and hope to see you at another UCAN event soon.